students, we start with lecture number 22. We are almost through with the phase diagrams. You may have noticed that while discussing the phase diagrams, I never talked to you about Gibbs phase rule. I never talked because it's not necessary. But you can discuss Gibbs phase diagrams, any phase diagram, using Gibbs phase rule. So before we move into geochemistry, I would give a talk today about the Gibbs phase rule. It's not about its application, maybe one or two applications. It's not because application of Gibbs phase rule to igneous rock is much more simple than application of Gibbs rule to metamorphic rocks, which are much more complex systems. But I think it is important that I tell you about Gibbs phase rule. Some of you know it, and some of you just read it somewhere. But I think you should know it before we move into geochemistry proper. So today I will talk about Gibbs phase rule. Gibbs phase rule, essentially, I've sent you a PDF already, and I asked you the central equations, the central theory that is crucial for Gibbs phase rule is called the Gibbs-Duhem equation. SDT minus VDP plus sigma mu I dNi is equal to 0. That particular equation. That particular equation essentially relates to a particular phase component, a particular phase, and connects all the variables, intensive and extensive variables, into one equation. So the total number of variables, say there are 9 variables, and you have one equation, say 9 variables, and you have one equation, then one of the variables, if you say for 9, if you know 8 of them, you can find 9, because they always add up to 1, because the total is equal to 1. So if you have one equation and 8 variables, then the actual number of variables to be quantified is 8 minus 1, because the equation itself helps you to get one variable if all others are null. So today we talk about Gibbs phase rule, and it has a very famous form, which is F is equal to C minus P plus 2. But the more important aspect of this phase diagram is to realize that the degree of freedom, what is the meaning of it? That is more crucial. The degree of freedom is the number of variables minus the number of equations. That is the catch. Number of variables minus the number of equations. That is the important point here. If it's for a metamorphic rock, you could call it number of metamorphic variables. If it's for igneous rock, you call it number of igneous variables. But essentially, these variables are thermodynamic terms. Have you understood? These variables are essentially thermodynamic terms. Say for example, NaAlSi3O8 in plagioclase is equal to NaAlSi3O8 in melt. If I write this equation, then thermodynamically at equilibrium, del GRPT is equal to 0. It is del H0 minus T del S0 plus P into delta V0, all of them in terms of reactions, plus, remember our simplified way of doing it, and RTLN, activity of, this is I'm calling albite in melt, divided by activity of albite in in plagioclase. Do you understand? So, if we take ideal solutions, which I always say, it's better to take ideal solutions to understand it better. Activity is a little vaguish term because it involves another coefficient. So if we do that, then we have what is called mole fraction if we assume ideal mixing. It's not that they mix ideally, but it's easier to see through the equation. Now in this, all these del H0, del S0, they can be quantified at a particular pressure temperature condition. These are, remember, for the pure phases. Pure phase compounds. So all this can be determined. But variables are this: temperature, pressure, this one, and this one. There are 4 variables. These are the 4 variables that relate, that are important for characterizing this equation. These blue ones are the variables. I have not done T here because I have already said T is a variable. So the equilibrium is controlled by 4 variables, intensive variables. These are temperature, pressure, composition of albite in melt, and composition of albite in plagioclase. So this is what I mean by saying number of variables. Say for example, kyanite is equal to sillimanite. This reaction. Again, you can write del Gr Pt is equal to del H0R minus T del SR plus P into del Vr plus RT ln activity of Al2SiO5 in sillimanite divided by activity of Al2SiO5 in kyanite. Have you understood? So again here, temperature, pressure, this one and this one are the variables. Have you understood? But these are the metamorphic variables for the reaction, equilibrium for the reaction, for a particular equilibrium involving kyanite and sillimanite. Now here, sillimanite and kyanite are normally pure phases. Pure phases means activity of Al2SiO5 in sillimanite is equal to activity of Al2SiO5 in kyanite. These values are equal to 1. Now, this means there are 1, 2, 3, 4 metamorphic variables, yes, correct, unquantified. But due to some reasons, 2 of them are quantified. 2 of them are quantified. That is what is important. Because of some aspects, because of some way of occurrences. Actually, they are not. Because kyanite and sillimanite contain ferric iron. They may also contain chromium ion. So, in actuality, they are not pure. But we consider it pure phases because the amount of impurity is very small. That is all, nothing else. So, these are taken to be 1. So, there are 4 variables, out of which 2 are quantified. So, the number of variables to be determined are 2, namely temperature and pressure, because these 2 are pure. But this ease we don't have here, because all of them are solid solutions. Now, say for example for this, if you say X albite plagioclase equal to 1, that means that's a condition that you have imposed. That is a condition that you have imposed. So it is an equation. Basically, it is an equation. So what is happening is, so now from variables 1, 2, 3, 4, since you have imposed this, there are 3 unknown variables. Can you tell me which system we are working on? We are working on a simple eutectic system. What was it? You had an impure melt crystallizing a pure solid. Impure melt crystallizing a pure solid. This is a perfect equation for simple eutectic system. Have you understood? So that is what is about metamorphic number of variables, metamorphic variables. This will depend on the part of the phase diagram or the system as a whole, what you're working on. That depends. Now we come to the number of equations. Now this is a little tricky thing, since I am trying to finish it within one class so that you understand it. It will not be possible for me to derive this. But there is a very famous equation which tells you how many equations can be generated. How many equations? Say for example, very simply, you know this phase diagram. Sillimanite, andalusite, and kyanite. You know this phase diagram. This one is a reaction between kyanite is equal to sillimanite. This is a reaction where you have sillimanite, andalusite, and this is a reaction where you have kyanite equal to andalusite. And this is a triple point. This triple point is located at about 505 degrees centigrades and about 3.7 kilobars. This is the triple point, where kyanite, andalusite, and sillimanite are in equilibrium. Now, is there a way, this is a simple system, is there a way, is it that all 3 equations are necessary? My first this thing is no, all of them are not independent equations. Why? Let's say I have kyanite is equal to sillimanite, and then I have sillimanite equal to andalusite. If I algebraically add these two, then sillimanite cancels off, and you have kyanite is equal to andalusite. So it appears, although there are 3 reactions, all 3 reactions are not independent. Some of them are derivative reactions. Yes? So is there a way where you can find out the number of independent reactions in a system, no matter how complicated the system could be? Yes, there is. I will, without the derivation, the answer to this question is number of independent reactions. Independent reactions in a system at equilibrium. If I do this, this is number of phase components minus number of system components. So no matter how complex is the system, it doesn't matter. The number of phase components, you calculate the phase components and subtract it from the number of system components, and you will get the number of independent equations, no matter how complex is your system. So this is a way by which you can find out number of equations and number of variables. So number of variables I've already talked to you. These are the reactions, these are the variables that characterize a particular equilibrium. But number of equations, number of independent equations. And how do you find out number of equations? By the simple formula. Number of independent reactions in a system at equilibrium is equal to number of phase components minus number of system components. Let's try it. So, let's try it. Ideally, if a system has three metamorphic variables, unknown metamorphic variables, or unquantified variables, then you will need three equations to find it out. Have you understood? That's an ideal situation. If you have three variables to determine, you need three equations to find it. That's it. If you have two equations, three variables and two equations, then the variance is 1. Have you understood? If there are three variables and two equations, then the variance is 1. Degree of freedom is 1. What does that mean? That means that one variable cannot be determined. You have to put in the variable. Have you understood? You need support from outside the system. That particular one value, if you can quantify, the rest of the values can be quantified. That is what the logic is. Have you understood? We will try to understand this from this simple formula. Its derivation is not very simple, but anyway, this is a very simple formula. So let's see. Let's take this point case 1. Case 1. What are the number of phase components? The number of phase components. What are the number of phase components? Let us consider kyanite and sillimanite are pure phases. So if they are pure phases, there are each of them has one phase component. So for case 1, phase component, I will write it PC here if you don't mind. PC equal to 1. PC equal to 2. At this point here, and SC, system component, is equal to 1. Because what is the component? Al2SiO5. So now, the number of reactions, therefore, is equal to 2 minus 1 is equal to 1. Number of phase component minus system component is equal to the number of reaction is 2 minus 1 is equal to 1. What is the reaction? Kyanite is equal to silver. That's the reaction. Have you understood? I will do it. I will go to this reaction again. It would be del GRPT equal to del H0R minus T del S0R plus P into del Y0R plus RTLN, activity of Al2SiO5 in sillimanite divided by activity of Al2SiO5 in kyanite. Now we have taken the system as Al2SiO5. Yes or no system component is Al2SiO5. So these are pure. So this will go off. Both are equal to 1. They are already quantified because the way you have put the system, it's quantified. It's quantified. Have you understood? So we have unknowns are temperature and pressure. Remember, this is equal to 0 at equilibrium. So the unknown variables are temperature and pressure. What does this say you? That you will have one equation. You have one equation and there are two variables. So you cannot find two variables from the same one equation. You can find one variable. But then the other variable has to come out from there. Somewhere else, you have to quantify it. So, this one, if you quantify one of the variables, the other variable can be determined. Say, for example, you say, this is my pressure. Now, this is the pressure. That means you are adding P is equal to some value. That's an equation. So, you're adding an equation. And if you can find out P, you will be able to find out T. Or if you give a value here, you will be able to find out. Have you understood? So that is the most important. Let's look at the triple point. I will erase this. Let's look at the triple point. What's happening here? Let's say this is point 2, case 2. So let's say case 2. Phase component. First let us do system component, that is better. System component still remains 1 L to side 5. Phase component equal to 3 because there are 3 pure phases, so they will have 3. Each of them will be 1 phase component. So the number of reactions, 3 minus 1 is equal to 2. There you are. So any 2 of the 3 reactions are independent. The third is a derivative. Have you understood? The third is a derivative. You can choose any 2, but the third will always be a derivative. So the number of independent reactions will be 2. Now, so let's say if we take kyanite and sillimanite, let's say we take kyanite and sillimanite reaction, and we take kyanite is equal to andalusite reactions. You will have, let's say, 2 reactions. We can't take the third because it becomes a derivative. Or you could have chosen these 2 and this would have become a derivative. It doesn't matter. Thermodynamics is a very sweet subject. It can reject very smilingly. It believes in numbers. Nothing else. So, if I take this, then what are the variables? Remember, kyanite and sillimanite are pure phases. So what will be the variables? Pressure and temperature. Kyanite and andalusite, they are all pure phases. So the variables will be pressure and temperature. Now you can see here, you have 2 equations and 2 variables. You will be able to quantify both. You will be able to quantify both. You don't have to get any information from outside. That means degree of freedom is 0. Degree of freedom is 0. Because you do not need a variable from... Take this Gibbs phase rule. Here, for this case 2 will be 3 minus, 1 minus 3 plus 2 equal to 0. The triple point is called invariant. Invariant means degree of freedom is 0. What is degree of freedom is 0? That means there are no unquantified variables. All of them are quantified. All variables are quantified within the system. You do not need to bring in a value from outside and then try and solve the case. You don't need it. It's self-quantified. That is what you mean when you say invariant. But when we were at case 1, it was univariant. Univariant. Why? Because F is equal to C minus P plus 2. This would have been 2. And so you would have landed up with 1. That means one of the variables, either pressure or temperature, had to be quantified to get the other one. Because you are essentially lying on this line and you don't know where on this line is your equilibrium. It contains kyanite and sillimanite. That means your equilibrium is on this reaction. But where? So if you quantify a pressure, you get a temperature, or you quantify a temperature, then this point becomes fixed and you get pressure. So that is important thing to remember. Remember, the Gibbs phase rule essentially is degree of freedom. That is the number of variables minus the number of equations, which means the number of unquantified variables. If both of them are the same, then it is self-quantified. Variance is 0. But if the number of variables are more than 0, 1, 2, 3, 4, so you have bivariant, trivariant, quadrivariant, and so on and so forth. So many variables are needed to quantify the system. So many variables are needed to quantify the system. That is it. Now, let's do one thing. So let's go into some of these phase diagrams that we have discussed, and let us see what we can do with this. We can take arbitrarily let's say now, we will now look at this phase diagram, very interesting, and we will end up in a very tricky area. Very, very tricky area. Anyway, let's say this is case 1. This is case 1. Remember in this diagram, what were the conditions? Both A and B minerals are pure. That means both minerals A and mineral B are pure. That's the first and the most important point. But the melt is impure. Yes or no? The minerals that crystallize are pure, but the melt is not pure. Right? So, what is that? Say for example, case 1, degree of freedom. What is it? It is C minus P plus 2. So what is the component here? System component 2, because it's A and B. F is equal to C minus P plus 2. So for case 1, what is C? There are 2 components. Okay? There is another problem. Remember, all these are done at isobaric conditions. You know, pressure was constant. We always said pressure was same, we always used to say. So here, we will have plus 1. Now, I will tell you this. One way of looking at it is, instead of 2 I am writing 1 means, 2 is for pressure and temperature. 2 is for pressure and temperature. Right? So now when I say my pressure is quantified, that means P is equal to something. So that means I have quantified the pressure. That is why one variable goes off. So that is why you have now 2 plus 1. At this point, how many phases are there? How many phases? Pure A, pure B, and the liquid. Yes or no? Pure A, pure B, and the liquid. So you have 3. So then you have 0. So you will say, this is invariant. No. This is isobaric invariant. Isobaric invariant. If you did not take the pressure as constant, then this eutectic point would vary as a function of pressure. So it is invariant. Actually, eutectic point is univariate. But because we draw the diagram in this way, because we take always an isobaric section, that is why this value 0 means isobaric invariant. But actually, it is univariate. Have you understood? What about any point here on this point? At about here in this point? Anywhere? So you can say f is equal to, now you see here, C remains 2, thus system component. This C is, remember, system component. C is equal to 2 minus P, two phases, liquid and A. Liquid and A. So you have 2 minus 2 and then you have plus 1. So this is degree of freedom is 1. Remember again, this is isobaric univariant. Isobaric univariant. Because this is a isobaric section of a surface. Isobaric section of a surface. That means you have cut it perpendicular to the pressure axis. So this one that you are saying is univariant is rubbish. Actually it is bivariant. It has a variance of 2. Why is it a variance of 1? Because I have reduced 2 to 1. Why did I reduce it? Because I said pressure I know. So you have quantified a variable. So you have cut down the variance by 1 purposefully. So that is why I am saying that f is equal to 2 minus 2 plus 1 is 1. You have got a univariant, but don't forget to write before isobaric univariant. If you just write univariant, you get a 0. Because actually it is bivariant. Now let us see, you take a case here. 3. So case 3 here, now this was case 2. So we have now case 3 and your f again is 2. A and B are the two phase components minus the number of phases. How many phases are there? There's the liquid. So 2 minus 1 plus 2 should be actual. Have you understood? 2 should be actual. That means this has a variance of actually 3. This is a trivariant system. But because this is an isobaric section, this is 1. And therefore, this is 2. So this is isobaric bivariant. But actually, it is trivariant. Have you understood? Now, you can ask me, sir, you are saying that bivariance, the variance is 3. Let's say if we take 2, the variance is 3. What are the variables? Fine, tell me, what are the variables? What are the variables? If there are no solids, at this point, case 3, there are no solids. So what is the variance? What are the what are the variables? XA in the melt. Then remember, this is 1 minus XB in the melt. So A, XA and XB are not independent variables. They're dependent variables. So you have one variable is XA in the melt. The second variable is temperature. See, you see, if I ask you what is the composition of the melt, what is the temperature of the melt, this is temperature and composition. And then pressure. But if you replace 2 by 1, then you see this is quantified. And then you have 1 and 2 variables. 1 and 2 variables. So now, we can say now, from this it's very clear that if you have case 3, this is a trivariant system or an isobaric bivariant system. Either a trivariant system or isobaric bivariant system. Right? What are the variables? XA in the melt or XB in the melt, because XA plus XB is equal to 1. Temperature, pressure. These are the 3 variables. But if you take isobaric, that means no pressure. That means there are 2 variables. So now you can ask me, sir, okay, I understand that there are 2 variables, but how do I write an equation? What is the number of equations? Let's see. Number of equations is phase components minus system components. Right? Fine. So, for case 3, what are the number of phase components? What are the number of, how many components are there in the phase melt? There are 2 components. Is it not? What are the 2 components? GA, GB, there are 2 components. Number of components is 2. Their mole fraction is equal to 1. That is different. But the number of components is 2. How many system components? A and B. The number of equations? 0. There are no equations. Of course, if you just have a melt, you have no equations. You have no equations. So that is why, because you have no equations, both these 2, for an isobaric section, both these 2 has to be quantified externally. The system cannot find it, because this case 3 is over this point. The whole of this field is case 3. It can be here, that means TXO2, another value, another value. The system cannot decide. You have to tell the system. You have to tell the system where the system is at the moment. That means you have to, if you specify temperature, still you see, you can have different XCA values. You don't get one XCA values. If you say here, down, then you quantify it. So this is your temperature and this is your XAB. And there are no reactions. So you will have no reactions. Okay. Now, let's go to something quite tricky here. Even for this system, tricky. Very, very tricky. Okay. There are another 1 or 2 points I will talk and then I will go. Let's say we are here. Let's say this is case 4. Case 4. Have you understood? Let's say this is case 4. Now, you know, phase diagrams, you've got to be very, very sneaky about things. Very sneaky. You've got to have a very sharp nose in smelling the problems. You have here. What does it mean? How many? So you have F is equal to C minus P plus 2 for case 4. Yes or no? So what is my C here? The answer is not 2. The answer is 1. Why? Because I'm all at this end. That means XA is equal to 0. So I'm behaving as a 1 component system. Have you understood? It's a 1 component system. So C here is equal to 1. What is P? What is number of phases? At this point, what is the number of phases? What is the number of phases? Pure A crystal and pure B melt. pure B crystal in equilibrium with pure B melt. So there are two phases. 1 minus. And then you have this eternal problem plus 2. That means 1. Have you understood? 1. Or if you say, no, I don't like it. I would like to make it isobaric. It's isobaric. 0. This 0 is isobaric invariant. This point here and this point here and this point here have the same status in terms of the Gibbs phase rule. All of them have degree of freedom equal to 0. Degree of freedom equal to 0. How many equations can you write here? What are the metamorphic variables? I had written this before. Say B solid equal to B melt. So del GRPT equal to 0 equal to del H0 minus RT del S R0 plus P delta VR0 plus RT ln XB in melt divided by XA XB in solid. Right? That's the equation. Do you get it? That's the equation. So what are the variables? Like before, temperature, pressure. Is XB melt a variable? No. XB melt is 1 because the system is 1. Pure A, pure B. So this is pure. And this one is also pure. There is no A in the system. So both are pure. So the variables are temperature and pressure. Is there an equation that you can write? I've already written it, so you can guess it. Yes, you can write. Number of reactions is equal to phase component minus system component. What is the phase components? 2. Why? 1 is for the B melt is a phase component and B solid is a phase component. So 2 phase components. How many system component? System component is B minus 1. You can write one equation. Here it is. I've written it. Here it is. So, this is how you need to be very critical of things. You have to be very, very critical of things. Don't go and do phase diagram in a very blatant, stupid way. You don't get it. You have to use it very, very cruelly. You have to be very precise in your thoughts. Very precise. Now let's say I ask you, what is the variance here? Let's say case 5. Now we come to case 5. What is case 5? A solid plus B solid. There are no minutes. A solid plus B solid. Now, it is a mixture of A and B. Gibbs phase rule does not apply to mixtures. They apply to equilibrium. But anyway, let's say at case 5, what will happen? F is equal to C minus P plus 2. Components 2, phases 2, so variance 2. If you slice this off to 1, then this becomes equal to 1. So variance is 1. What is the variance? What is the variance? You can be anywhere in your field. You can be anywhere in your field. That means P and XA or XB, these are the variables. But XA and XB, these are to be equal to 1 because both the solids are pure. So you have only temperature. Have you understood? Tell me, have you understood? At this point, A and B are pure A and pure B. It's a mixture. Like sillimanite and kyanite. It's a mixture. And you can be anywhere in this field. You can be anywhere in this field. That means you can have a particular T value, you can have a particular X value, so you will be here. If you change the T value, you will have somewhere here. So it could be anywhere here that the variables will be T and XA. What is XA? XA is 1. Because for A, XA is 1. For B, B is a pure phase. What about XA and XB? There are no XA and XB. Because both are pure phases. Both are pure phases. So there is a problem here. Although this says that you just can't fix the T and you will get XA and XB, you have to fix that. You have to fix one variable. That means one variable. Say I fix temperature, I should get XA and XB. No, I don't get. I don't get XA and XB unless you are talking of XA and XB as a proportion of A and B. As a proportion of A and B, not composition. We don't give mole fraction as a proportion. We give mole fraction as a mole fraction is a mole fraction in a phase. For a proportion, we don't use the term say. So there is a problem here in dealing with mechanical mixtures. It's a fallacy. But because you cannot explain mechanical mixtures using this type of expression, this type of a phase diagram. Just to complete this, say for example, so you can apply this to different phase diagrams and ask yourself the questions. The questions are very simple. One is, what is the Gibbs phase rule? That means you have to know your system component, better know your system component. Or for example, system component, or for example, phases, number of phases. What are the number of phases? This you need to know, and whether it's isobaric, whether it's non-isobaric, this will give you the phase rule. Then you have the metamorphic variables. Proportion is not a metamorphic variable. Mole fraction is a metamorphic variable. And so is pressure, temperature, conditions a metamorphic variable. So for a system, identify the metamorphic variables. Once you have done it, Gibbs phase rule is number of variables minus number of equations. First find out the variables, and then you find out the number of equations. How do you find the number of equations? These are independent reactions. Those are independent reactions. How do you find it? Phase component minus system component. That's it. Phase component minus system component. That is how you find out the reaction. Let's say, we'll do this as the last phase diagram and then we will move on. If you have problems, you call me, or if you have certain specific problems while dealing with certain specific phase diagrams, then you can write to me and I could take a visual class giving you a problem and saying and trying to solve it if I can solve. Okay? Or I could tell you where you had gone wrong, so that I can do. So otherwise I will try to answer the question myself over the global class. You remember? This phase diagram. We have done this before. There's a peridictic relation and the eudectic relationship. let's say we take the case here, 1. Remember in this diagram that we started, all 3 are pure phases. All 3 are pure phases. So if you take case 1, then you have F is equal to C minus P plus 2. And so the number of components are A, B, and C. So the phase components are 3. How many phases? A, C, B, and the liquid. So the number of phases are 4 plus 2. So this becomes 1. But as is customary, this becomes 1, then this becomes 0. So, no other reactions or equations are necessary to quantify the variables. What are the variables? What are the thermodynamic variables? That is the most important. Pressure, known. Yes or no? No. Temperature, known. How? Isotherms. Then X, A in A, known. Pure phase. XA, XB in B, known. Pure phase. XC in C, known. Pure phase. All components are known. Not the proportions, the thermodynamic components are known. You don't need anything to quantify the system. If you had pressure, then you would have it under control. Yes, you would have it. So say for example, similarly, let's say this is case 2. You can try it for any phase diagram. In fact, I will ask you to do it so that you generate more confidence. Say case 2. So in case 2, F is equal to C minus P plus 2. What are the number of components? 3. What is the number of phase? B. What is the number of phase along this? B plus liquid. You see, this is B plus liquid. Oh, sorry. This is D plus liquid. This is B plus liquid. So, along this line, there are 3. B, D, L. 3 plus 2. So, this will be degree of freedom 2. This will be degree of freedom 2. And if you take an isobaric section, this will be 1, this will be 1. What is one variable needs to be constrained? Can you tell me what is the metamorphic variable? How many equations? Let's see. Number of reactions is equal to phase component minus system component. Remember, 1, 2, 3. 3 is the phase component, 3 is the system component, 0. Number of reactions is none. No reactions. Say here, B, D, and L. B has a single phase component. Have you understood? So what I will suggest to you, that you try to do it yourself. When you get stuck, you place me, let me know. You remember, in a ternary system, a melt comprises of all the 3 components. Remember? All the 3 components. So there are phase component, XA melt, XB melt, XC melt. These are the composition, not proportion. Composition of melt. Say A contains 30% melt, 30% A, 20% B, etc., etc. What are the reactions? So you write the reactions. There will be some more reactions. What I have said here is very simplistic. It's wrong. You try to do it. If you have problems, please let me know. Or else I will take, if I can't tell you on the Google Classroom, then I will take a visual class and I'll try to explain to you. Okay? Thank you very much. Thank you.